Welcome to mathematics class. I am Julia Alalibo, and today we'll be studying the theme Algebraic Operations, and our topic for today is Quadratic Expressions Part 2. Now, by the end of this lesson, you should be able to expand and factorize expressions involving perfect squares, expand and factorize expressions involving difference of two squares, and solve simple word problems using factorization. So, perfect squares. Now, in the part 1 of this lesson, we've dealt with factorization, how to expand, and then how to factorize. In this lesson, we'll be dealing with perfect squares and difference of two squares. Now, what's a perfect square? Let's look at this here. A minus B all squared. If we are asked to expand this, what we normally do is do A minus B. Since there's a square here, it means that this occurs twice. So we do A minus B times A minus B. And then we do the expansion, or to find the product, by doing A times A to get the first term, and then minus B times minus B to get the second term. Then minus B times A plus A times minus B to get the middle term. But all this is just a long process because this is a perfect square. So when we are dealing with perfect squares, there is a particular order which they follow. Rather than going through this process of multiplying A by A, minus B, and then finding the sum of the middle term and the outer terms. So we are going to be dealing with how to expand perfect squares. Now, in the previous lesson, the part 1 of quadratic expressions, we had things like, say, 3x plus y all squared. Now, to do this, we'll normally say 3x plus y and 3x plus y, and then find the product of this. But notice that what is in the bracket, the two terms, the two binomials, are the same. So rather than multiplying or expanding it this way, once we multiply this, we are going to get something of this nature. For instance, a minus b all squared, we got a squared minus 2ab plus b squared. Now, to get the expansion of a perfect square, let's look at the first step to note. The square of the difference of two terms is equal to the sum of their squares minus twice their product. This is what I mean. We have a minus b all squared. Now, to expand this, we don't have to go through this process. All we have to note is that to get the expansion of this perfect square, a minus b, which can translate to a minus b times a minus b, we simply say it is equal to the difference of the two terms. So the square of the difference of the two terms is equal to the sum of their squares. That is, the first term is a and the second term is minus b. So a minus b all squared is equal to the sum of their squares. That is a squared plus minus b all squared minus, because this is what is in the bracket. The sign in the bracket is minus. So you will now say minus twice their product. That is 2 times a times b. And this will give us the expansion of a minus b all squared. So whenever there is a problem, when we have a perfect square, that is a minus b all squared, where the both terms in the bracket are the same, we don't have to go through the long process. We just say the square of the difference of two terms is equal to the sum of their squares minus twice their product. So to expand a minus b all squared is equal to the sum of the squares a squared plus minus b squared minus twice, 2 times their product. Their product is a times b. And the same thing applies for the positive one, a plus b all squared. This will be equal to the square of the sum of two terms is equal to the sum of their squares plus twice their product. So if you have a plus b all squared, this will be equal to the sum of their squares, the individual terms, the squares, that's a squared plus b squared. Then we take note of the sign. This is positive. So it now becomes plus twice their product, 2 times their product, 2 times A times B. So this is how a perfect square is calculated when you're asked to expand a perfect square. Now let's look at some examples that will help buttress this point. We are asked to solve m plus n all squared. Now this can be expanded to mean m plus n times m plus n. Now notice that the two terms in the brackets are the same. So we simply use our law here, which says the square of the difference of two terms is equal to the sum of their squares minus or plus twice their product, depending on the sign given. So for our example here, the sign here is positive. So m plus n all squared is equal to the square of m, which is the first term, plus twice the product of m and n, that is 2 times m times n, plus the square of n. You can say the square of m plus the square of n plus twice the square of their product. Then we rearrange it after we've solved it. So this is what it looks like. M plus n all squared will be equal to m squared plus, because the sign here is positive, plus 2 times m times n. This m and n here is the m and n that was given in the question. So 2 times m times n plus n squared, which is the other term in the bracket here. And once we expand this, we have m squared plus 2 times m is 2mn plus n squared. So this is the expansion of m plus n all squared. Because m plus n is a perfect square, though the expansion is m squared plus 2mn plus n squared. Now let's look at another example where we have a negative sign. Now solve 6a minus 5b all squared. This is equal to 6a minus 5b times 6a minus 5b. And when we have perfect squares, the law says that it is equal to the square of the first term plus the square of the second term. Then depending on the sign in the bracket, minus or plus twice the product of the terms. Now for 6a minus 5b, to expand this, we will have the square of 6a, which is 6a squared, minus twice the product of the two terms, that is 6a and 5b. Minus, because what is given in the question is a negative sign. So minus 2 times 6a times 5b plus the square of the other term, that is minus 5b. And once we expand this, 6a squared is equal to 36a squared, because 6a times 6a is equal to 36a squared. 2 times 6a times 5b is equal to minus 60ab. And minus 5b times minus 5b is equal to 25b squared. Now, some other examples here. Expand 2 minus d all squared, 3v minus 2u all squared, 5a plus 3c all squared, and 3 plus 10 all squared. So for the first one, first of all, we take note of the sign in the bracket. It is a minus sign. And this is a perfect square because 2 minus d all squared is equal to 2 minus d times 2 minus d. So, to get the expansion of 2 minus d all squared, we do this. For a perfect square, it's equal to the sum of their squares, that is 2 all squared plus minus d all squared. Then we take note of the sign, minus twice their product, 2 times 2 times d. So this will now be equal to 2 times 2, or 2 squared is equal to 4, minus d squared is equal to plus d squared, and 2 times 2 times d will be equal to 4d. So the expansion of 2 minus d all squared, we can rearrange this to be 4 minus 4d plus d squared. So this is the answer for the first expansion. And now for the second expansion, 3v minus 2u all squared. So we have 3v square plus the square of the second term, that is 2u. So is it minus or plus? We take note of the sign in the bracket here. It's negative. So minus twice the product of the two terms, that is 3v times 2u. And then we simply calculate this. 3v times 3v will give us 9v squared plus 2u squared is equal to 4u squared minus 2 times 3v times 2u is 12uv. So then we can rearrange this to be equal to 9v squared minus 12uv plus 4u squared. And this is the answer for the second expansion. So for our third question, we have 5a plus 3c all squared. Now for a perfect square, this is a perfect square because if you expand it, it will be 5a plus 3c times 5a plus 3c. So to solve this or to expand this, we simply say the square of 5a plus the square of 3c plus twice their product. So for number 3, we have 5a all squared plus 3c all squared plus, because what is in the bracket here is positive, plus twice their product, that is 2 times 5a times 3c. So once we expand this, 5a times 5a, 5a squared means 5a times 5a. That gives us 25a squared plus 3c times 3c is 9c squared plus 2 times 5a times 3c gives us 30ac. Then we can rearrange it to be 25a squared plus 30ac plus 9c squared. Now for the fourth question, there's no letter, but it can still be solved, meaning that perfect squares can be used when solving for ordinary numbers, numbers without alphabets in them. So if we have 3 plus 10 all squared, we can simply say the square of 3 plus the square of 10 plus twice their product, that is 2 times 3 times 10. So 3 squared, that is 3 times 3 is 9. 10 squared, 10 times 10 is 100. And 2 times 3 times 10, this is 60. So 9 plus 100 plus 60 gives us 169. So the answer to the fourth question, 3 plus 10 all squared, is 169. And if we look at it, this, 3 plus 10 is actually 13. So this is also equal to 13 squared. To check if we are right, this is 3 plus 10 is 13. So the question is actually find 13 squared. And 13 times 13 gives us 169. So perfect squares can be used when solving for ordinary numbers too. Now, expansion of perfect squares can also be used in finding the square of numbers. So let's take our first example here. We're asked to find the square of 109. If we do not have a calculator to punch this, we can simply use perfect square to solve for the square of 109. Knowing that 109 is the same thing as 100 plus 9. Right? So this is what we have here. 109 squared is the same thing as 100 plus 9 all squared. So using the law of perfect squares, the square of 100 plus the square of 9 times twice their product. So what do we have here? We have 100 squared plus 9 squared plus 2 times 100 times 9. So 100 times 100 gives us 10,000. 2 times 100 times 9 gives us 1,800. And 9 times 9 gives us 81. Once we add all this together, we have 11,881. So the square of 109, if we do not want to use long multiplication, or for the purpose of this topic, we have 11,881. Now look at the next example, 195 squared. We can say 195 is equal to 190 plus 5. But the essence of using factorization is to simplify. If I say 100, this is correct, this is quite correct. If I say 195 all squared is equal to 190 plus 5 all squared, this is quite correct. But the purpose of factorization is to simplify. And if I have 190 and I'm asked to find the square, because to do this we have to find the square of 190, the square of 5. To find the square of 190 might be cumbersome. So we use a number whose square is easy to find, knowing that 195 is also equal to 200 minus 5. And finding the square of 200 is easier than finding the square of 190. So we use 200 minus 5. 200 minus 5 is the same thing as 195. So using the law of perfect squares, we have 200 square minus, because what's in the bracket here is minus twice their product, that is 2 times 200 times 5, plus minus 5 all squared. So the square of 200 is 40,000. If we do this multiplication here, 2 times 200 times 5, this gives us 2,000. We bring down our negative sign, which is here. And minus 5 times minus 5 gives 25. And once we do this summation here, by doing the addition here, that's 40,000 minus 2,000 plus 25. 2,025. So once we do this, 40,000 minus 2,025, we get the answer, which is 38,025, which is the square of 195. So expansion of perfect squares can be used in finding the square of ordinary numbers. Now, let's look at this example. We are asked to factorize s squared plus 20s plus 100. In part 1 of this lesson, if we were to factorize this, we would have done this, say, 2 brackets, fill in s, then look for 2 numbers whose product is 100 and whose sum is 20. But let us notice something about this particular question. We notice that s squared is the square of s, or we can say the square root of s squared is equal to s from the first term. Then let's look at 100. 100 is the square of 10, or the square root of 100 is equal to 10. And then we look at the middle term here. If we say 20s, from looking at the middle term, 20s, it is twice the product of 10 and s. This 10 and s we have here. If we say 2, twice the product, 2 times 10 times s. This will give us 20s. And what does this remind us of? A perfect square. Because when we were handling perfect squares some minutes ago, we said, for instance, we have s plus 5 all squared. To expand this, we simply say s squared plus 5 squared plus twice their product, 2 times 5 times s. And this gives us s squared plus 10s plus 25. Now, there's a little bit of similarity between this perfect square and this factorization here. So once we notice this, that s squared, the square root of this s squared, the first term is s, the square root of 100 is 10, and the middle term is actually twice the product of s and 10. It's safe to say that this was gotten as the product of 2 terms. This was gotten as the expansion of a perfect square. So if this is established, we can say that s squared plus 20s plus 100 is equal to s plus 10 times s plus 10, and this is equal to s plus 10 all squared. So to factorize s squared plus 20s plus 100 is x plus 10 all squared. And if we want to expand this to be sure, all squared, we have this, since this is a perfect square, say s squared plus 10 squared plus 2 times s times 10. And this gives us s squared plus 100 plus 20s. We can rearrange it to be s squared plus 20s plus 100, which is the same as what we have here. Now another example, factorize 4x squared minus 3x plus 64. Again, notice that 4x squared is the square of 2x. 64 is the square of 8. And 32x is twice the product of 8 and 2x. That is 32x is equal to 2 times 8 times 2x. So we can simply factorize by saying 4x squared is equal to 2x minus 8 times 2x minus 8. This minus sign here is because 32x has a minus sign. And just like we did in the previous example, the sign here follows the sign which is given in the question. So 4x squared minus 32x plus 64 is equal to 2x minus 8 times 2x minus 8. And this is equal to 2x minus 8 all squared. Now express the following as squares in the form a plus b all squared. That's express this as perfect squares. So for the first one, a, 4f squared. The square root of 4f squared is 2f. The last term, the square root of 9 is 3. And then we also notice that 12f is equal to twice the product of 2f and 3. 2 times 2f times 3 gives us 12f. So it is safe to say that 4f squared minus 12f plus 9 is equal to 2f minus 3 times 2f minus 3. This minus sign here is because the 12f carries a minus sign, and this is equal to 2f minus 3 all squared. So this is the simple factorization of 4f squared minus 12f plus 9. We have represented it in this form, a plus b all squared. Now for the second one, 30nv plus 25n squared plus 9v squared. Now before we start, we can simply rearrange this to look like number 1. So 30nv plus 25n squared plus 9v squared is also equal to 25n squared plus 30nv plus 9v squared. Now, the square root of 25n squared is 5n. The square root of 9v squared is 3v. And then 30nv is equal to 2, that is twice the product of 5n and 3v. So we can say the factorization of 25n plus 30nv plus 9v squared is equal to 5n plus 3v plus, because 30nv carries a positive sign, times 5n plus 3v, which is equal to 5n plus 3v all squared. So the solution to 30nv plus 25n squared plus 9v squared is 5n plus 3v all squared. Now we have to note that when solving things like this, when we are asked to express this in this form or we are asked to factorize, not all cases will lead to perfect squares. So if we try take the first term and we find the square root and it gives us maybe 2f, we take the third term, we find the square root and it gives us 3. But then the middle term is not twice the product of the square roots we found. Then we have to know that that expression or that question will not yield a perfect square. So then we have to use the normal factorization method where we open two brackets, fill it with the first letter, say f, and then find two numbers whose product is the last term and whose sum is the middle term. So not all expressions lead to perfect square. Once they don't fulfill these conditions, where the first term has a square root, the last term has a square root, and twice the product of those square roots gives the middle term, then that will not lead to a perfect square. We have to use the normal factorization method that we've learned in part 1 of this lesson. Now, difference of two squares. A binomial that has two perfect square terms that are subtracted is called the difference of two squares. Now, let's say we have a square minus b squared. This is called the difference of two squares. Know that a is a perfect square, b is a perfect square. Once they are subtracted, two perfect squares, say a square and b square, once they are subtracted, we say this is called the difference of two squares. Now, let's look at this. Supposing we have a plus b times a minus b. A plus b times a minus b. And we're asked to find the products of these two terms, a plus b and a minus b. Using our normal expansion method, we say a times a, this gives us a squared, which is what we have here. Then multiplying the last two terms, b plus b times minus b, we have minus b squared. Then adding the inner term and the outer terms, adding their products. So we have b times a gives plus ab. And then a times minus b gives minus ab. Once we do this, we have a squared. ab minus ab, that is 0. So we just have a squared minus b squared. And this is the difference of two squares. So this, what we did here, is simply what is here. A plus b times a minus b gives a squared plus ab minus b squared to result in a squared minus b squared. So we can take it in reverse to say the difference of two squares is equal to the product of their sum and their difference. The difference of two squares, that is a squared minus b squared, is equal to the product of their sum and their difference. What do I mean? The difference of two squares, a squared minus b squared, is equal to the product of their sum and their difference, meaning that a squared minus b squared is equal to the product of their sum, the sum of a and b, and their difference. The difference is a minus b. So whenever we have something that looks like this is called the difference of two squares, and the factorization is simply a plus b times a minus b. Now we have to note that a squared minus b squared, which is difference of two squares, is not equal to a minus b all squared. So if we have something like this, let me say we have 5 squared minus 3 squared. Someone might be tempted to say this is equal to 5 minus 3 all squared. This is not correct. This is the difference of two squares, and this looks like a perfect square. If we are to solve this, 5 squared minus 3 squared, that is 25 minus 9 is equal to 16. And if we are to do this, we have 5 minus 3, that is 2. And 2 squared will be equal to 4. So 16 is not equal to 4. So what I'm trying to say is that a squared minus b squared is not equal to a minus b all squared. We also have to note that the difference of 2 squares does not apply to the sum of 2 squares. So we cannot say a squared plus b squared is equal to ab times ab. This is not correct. It only applies to the difference of 2 squares. That is a squared minus b squared. Now let's look at some examples here. Factorize d squared minus 6 squared. Simply equal to, remember from our previous slide we had a squared minus b squared. This is the difference of 2 squared. It is equal to a plus b times a minus b. So anything of this form, this is the factorization. So if we have d squared minus 6 squared, to factorize this, we simply say is equal to d plus 6 times d minus 6. Now for 4y squared minus 25, we have to find the square root of 4y squared and make 4y squared to be in this form, a squared minus b squared. So once we have that, the square root of 4y squared is 2y. So we have 2y squared minus the square root of 25 is 5. So minus 5 squared. Now 2y squared minus 5 squared is in this form, a minus b squared. So we can simply say 2y squared minus 5y squared is equal to 2y plus 5 times 2y minus 5. Once we are given any question that looks like a difference of 2 squared, we must first of all make it to be in this form, a squared minus b squared. Notice that the 25 here is not in this form of b squared, and also a is not in this form because this square here only applies to y. We must make it in such a way that the square applies to the entire term. So here we have 64 minus b squared. 64 is not in this form, a squared. So the square root of 64 is 8. So we can say 8 squared. Now it is in the form a squared. So we have 8 squared minus b squared. And the simple factorization is this. 8 plus b times 8 minus b. And now for d, we have 9e squared minus 16f squared. It is also not in the form a squared minus b squared. So we make it to be in this form by finding the square root of 9e squared. The square root of 9e squared is 3e. So 3e squared is equal to 9e squared because 3e times 3e is equals to 9. E times e gives us e squared. So now we have made 9e squared to be in the form of a squared. That is 3e all squared. The same goes for 16f squared. The square root of 16f squared is 4f. So we put it in a bracket and then raise it to the power 2, making it 4f all squared. So we can simply factorize it, say, and the factorization will be 3e plus 4f times 3e minus 4f. The difference of 2 squares can be used to shorten calculations. For example, we have find the value of 66 squared minus 34 squared. 66 squared minus 34 squared is already in the form a squared minus b squared, and this is the difference of 2 squares. So this also is the difference of 2 squares. We can say this is equal to 66 plus 34 because factorizing a minus b squared is a plus b times a minus b. So this is 66 plus 34 times 66 minus 34. And 66 plus 34 gives us 100, while 66 minus 34 gives 32. 100 times 32 is 3,200. Now let's look at some word problems that lead to difference of 2 squares. A square piece of metal is cut in the center as in the figure below. Find the area of the part colored blue. So this is a square piece of metal. A hole was cut in the middle. A hole with length of 5 meters was cut in the middle of the square of 20 meters. And we are asked to find the area of the part colored blue. So what do? We know that the area of a square is equal to length times breadth. So the area of the actual square is 20 times 20, which is the same thing as 20 square. While the area of the part cut out, the yellow part, is 5 times 5, which is the same thing as 5 square. So we want to use the difference of 2 square to calculate the area of this part colored blue. So now the area of square A, that is the main square, we've said is 20 square, while the area of the square B is 5 square. Now to find the area of that part that was colored blue, that is this part here, we have to subtract the area of the whole from the area of the main square. So we have 20 square minus 5 square. That will give us the area of the remaining part that was colored blue. So to do this now, this looks like the difference of 2 square. It's in the form a square minus b square. So we simply apply the factorization of this, which is a plus b times a minus b. So we have 20 plus 5 times 20 minus 5. 20 plus 5 gives us 25. 20 minus 5 gives us 15. 25 times 15 is 375 meter square. So the area of the part colored blue is 375 meter square. Now another word problem. A man is 3 years older than his wife. The sum of their ages is 73. Now the question is, calculate the difference between the square of their ages. So we are told from the question that a man is 3 years older than his wife. So let's say the age of the wife is X. If the man is 3 years older than her, it means that his age is X plus 3. We do not know the age of the wife. So to calculate the difference between their ages, between the square of their ages, we have to first of all find the age of the wife, which we do not know. So the wife's age, let's call it X, while the man's age is X plus 3, since he is 3 years older than her. Now from the second statement, the sum of their ages is 73. So we have X being the wife's age and the man's age, X plus 3. We are told that the sum is 73. So to find X, we simply do the calculation. X plus X is 2X plus 3 equals to 73. 2X is equal to 73. Taking 3 over the equal sign becomes 73 minus 3. So 2x is equal to 70. Therefore, x is equal to 70 divided by 2, which gives us 35. And x is the age of the wife, which means that the wife is 35 years old, while the man is 35 plus 3. That is 38 years old. Now, the question which we want to solve is calculate the difference between the square of their ages. Now, from the calculation, we saw that the wife's age is 35, while the man's age is 38. The difference between the square of their ages, we have 38 square minus 35 square. Again, it is in the form of the difference of 2 squares, which is equal to, factorizing this is a plus b times a minus b. So we have, this is our a, this is our b. A plus b, that is 38 plus 35, times a minus b, that is 38 minus 35. This gives us 73, while this gives us 3. 73 times 3 is 219. So the difference between the square of their ages is 219. So the difference of 2 squares can be used in solving ordinary mathematical problems. Now we've come to the end of our lesson for today. And in summary, we learned that the following identities exist for a perfect square. So for a perfect square, when we are subtracting, a minus b all squared is equal to the sum of the squares minus twice their product. That is a squared minus 2ab plus b squared. So for a plus b all squared is equal to the sum of their squares plus twice their product. That is a squared plus 2ab plus b squared. We also learned that a binomial that has two perfect square terms that are subtracted is called the difference of two squares. And the difference of two squares is factorized as follows. A squared minus b squared is equal to a plus b times a minus b. And we also learned that a plus b all squared is not equal to a squared plus b squared. Now, before we go, we are going to look at a few test questions to see how well we've understood the lesson. So question 1, factorize 9 minus 6a plus a squared. Option A minus 9 all squared. Option B, a minus 3 all squared. Option C, a plus 3 all squared. And option D, a plus 9 all squared. So, without even solving this, you can get the correct answer. The first thing to do, we look at the sign in the middle. It's a negative sign. So that tells us that our answer cannot be any of the positive ones, because this is a kind of perfect square. This will give us a form of perfect square. So let's go. The first term, first of all, we rearrange this to be a squared minus 6a plus 9. We simply rearrange this. And then, look at our first term. The square root of our first term, a squared, is a. The square root of 9 is 3. And we can also notice that 6a is twice the product of a and 3. So, this is a form of perfect square. The answer will be a minus, because what we have in our question is minus 3, a minus 3. And this is equal to a minus 3 all squared. So the correct option is option B. Now for our second test question, a metal ring of radius 23 cm is fitted at the center of another ring of 37 cm radius. Question is, find the area of the space between them. A, 2,640 cm square. B, 600 cm square. C, 264 cm square. D, 60 cm square. So, you can solve this on your own, pause the video, solve it on your own, and come back to check for the correct answer. So to do this, we can draw this question or make this question in a pictorial form so we can understand it. This is a metal ring of 23 cm radius. Is fitted at the center of another ring of 37 cm. So it's fitted at the center of a bigger ring of 37 cm radius. The question is, find the area of the space between them. So the space between the two rings, that's what we have to find. And this is a circular ring. The area of a circle is equal to pi r square. So to find the area of this space, we simply subtract the area of the smaller circle from the area of the bigger circle. So let's say the radius of the bigger circle has a big R, while the smaller one has a small r. So the area of the space between them will be equal to pi r square, that is the area of the big circle, minus pi small r square, that is the area of the small circle. Now we can factorize this in this form. Taking out pi, we are left with r squared minus r squared. And the radii have figures attached to them. So this is equals to pi. The big radius is 37 square minus 23 square. And this here looks like the difference of two squares, which is a square minus b square. Factorizing a square minus b square is a plus b times a minus b. So we use the difference of two squares to solve this question. So pi is 22 over 7 times a plus b. Our a is 37, our b is 23. So 37 plus 23 times a minus b, 37 minus 23. This gives us 37 plus 23 gives us 60, while 37 minus 23 gives us 14. Sixty times 14 is 840. And then we can reduce this 7 into here 1. And what's left here is 120. So this is equal to 22 times 120. This is equal to 2,640 centimeter square. So the area of the space between them is 2,640 centimeters square, which is option A. We've come to the end of our lesson for today on quadratic expressions, part 2. I hope you understood the topic. Do have yourself a nice time. Thank you.